Have you ever tried pressing a suction hook onto your bathroom wall and watched it stick as if held by magic? Well, it's not magic, it's atmospheric pressure at work. Even though we don't see it, the air around us is constantly pressing against everything. And to help us truly grasp the power of this invisible force, physicists over the years have designed simple yet powerful demonstrations. These experiments show us that air is not empty, it has weight, and it can exert a force strong enough to crush metal or hold up water. In today's lesson, we'll explore a few amazing demonstrations that make this invisible pressure visible. As you'll see a seal can being crushed by outside air is just one of the many ways we can witness this powerful phenomenon. Let's begin with one of the most dramatic demonstrations, the crushing of a tin can. Here's how it works. A little water is heated inside a sealed can until steam is produced. The steam pushes out the air, and the can is then sealed and cooled quickly. Now watch closely. The steam inside condenses into water, leaving almost a vacuum inside. With little to no pressure inside the can, the external atmospheric pressure now acts unopposed and crushes the can like a soda can under a boot. This tells us just how strong the air pressure around us really is. As seen in the diagram, external arrows press inwards as the internal steam pressure drops, a stunning demonstration of nature's balance shifting. Now for something equally impressive, the inverted glass of water experiment. Here's what you do. Fill a glass to the brim with water, cover it tightly with a card, and flip it upside down. Surprisingly, the card stays in place and the water doesn't fall. Why? Because the atmospheric pressure from below is greater than the weight of the water above. That upward force supports both the card and the water. This is a clear example of how air pressure pushes in all directions, including upward, strong enough to defy gravity in this case. In the visual, we can see upward pointing arrows representing air pressure acting on the base of the inverted glass. Now think about a rubber sucker, those little discs that stick to glass or tiles. When you press one onto a wall, what really happens? By pushing out the air trap inside, you create a region of low pressure between the sucker and the wall. Outside, atmospheric pressure remains high. This pressure difference causes the outside air to push the sucker onto the surface, holding it tightly in place. This is exactly how vacuum lifters handle large glass panels, using the same principle on a larger scale. Check out the cross-sectional view here. The lower internal pressure is shown, with larger external arrows representing atmospheric force. Now let's step into a bit of history, the famous Magdeburg hemispheres experiment. In the 1600s, scientist Otto von Guericke fitted two hollow hemispheres together and removed the air from inside using a vacuum pump. What happened next amazed everyone. Even to teams of horses pulling in opposite directions couldn't separate the hemispheres. Why? Because the air pressure outside was so strong, and with no internal air to balance it, the hemispheres remained stuck together with incredible force. This public demonstration was one of the first to show that air has mass, weight, and exerts real pressure. As you can see in the diagram, arrows from all sides represent the external pressure pinning the two domes together. Let's now back this concept with a numerical example. Suppose we have a metal lid of area 0.2 square meters and the atmospheric pressure is 1.013 into 10 to the power 5 pascals. We are asked, what is the force acting on this lid? We use the formula force equals pressure multiplied by area. That's F is equal to 1.013 multiplied by 10 to the power of 5 multiplied by 0.2. Calculating that gives F is equal to 2.026 multiplied by 10 to the power of 4 newtons or 20,260 newtons. That's more than 2 tons of force all due to atmospheric pressure. And yet, it doesn't crush the lid because the pressure inside and outside is balanced. In the diagram, the lid is shown with arrows from above and below, demonstrating this equilibrium. So, what have we uncovered today? That air isn't just space between objects, it's a medium with mass capable of applying tremendous pressure. Through crushed cans, water that won't fall, and rubber suckers that cling like magnets, we've seen how this invisible force becomes visible. Remember the formula we used again and again? F equals P into A, where P is pressure in pascals and A is area in square meters. Atmospheric pressure acts in all directions, and it's responsible for everything from breathing to the functioning of barometers. I hope you now feel the weight of the air, not as a burden, but as a reminder of how fascinating physics can be. See you in the next session where we continue exploring the invisible, the incredible, and the absolutely real forces that govern our universe.